It's a real pleasure today to have a presentation from Chris Fred. And Christopher and Fred is a founding partner of Blue Angel Energy. And he also serves as a stimulation technical director for Resman Energy Technology. And so, in that capacity, he brings over 25 years of experience in stimulation, completions, and other technology integration, as a matter of fact, across the oil and gas sector. He currently leads innovative tracer interpretation for multi-stage fracture characterization. And this is a methodology that is deployed in unconventionals, and it is being used at the Utah Forge Enhanced Geothermal Project. Chris also served on the Geode Task Force for completions and stimulation. Previously, he held various senior technology leadership positions at SLB, and that included Technology Center Director and Global Business Development Manager. So Chris earned a PhD from Professor Fogler in chemical engineering from the University of Michigan, and he holds more than 30 granted patents and has 40 publications. So a real pleasure to introduce Chris Fred.
Well, thank you, John. Yeah, it's a pleasure to spend some time today and talk about the novel hydraulic fracture characterization that's been done at Utah Forge, and it's providing some unique insights on completion and stimulation designs that I think impact obviously EGS as well as unconventional plays. This presentation will be a combination of a couple of papers. One was an ERTEC paper that was presented a couple of months ago, and then a geothermal rising paper that'll be presented in October. So I'd like to recognize co-authors Chris DeSorf, Partho Giri, Sven Hartvig, Olaf Huizaby, all from Resman Energy Technology, John McLennan from University of Utah, and Kevin England as an independent consultant. So with that, just want to start with kind of a general introduction to enhanced geothermal systems, or EGS. I think as many in the audience know, this is basically leveraging horizontal drilling and multi-stage fracturing from the shale world and using it to construct a lot of surface area for heat transfer for geothermal applications. And you can just see an illustration here with two horizontal wells connected by several horizontal fractures along the length of those wellbores. We then inject water into one of the wells, circulate it through the fracture system, and produce steam. And then on surface, we're running turbines to generate electricity. There's a lot of innovation taking place in this space. See Utah Forge, or the Frontier Observatory for Research in Geothermal Energy. That's been laying a lot of the fundamental groundwork for new techniques and optimizing approaches for EGS. And then there's been a lot of activity with Fervo to take a lot of those concepts and scale them and convert it into commercial applications. And they're moving towards a 400 megawatt power generation by 2028. So with Resman, we've had the opportunity to work with John and the team at Utah Forge, and that's what we'll focus on here. To kind of set the groundwork, there was, the founding kind of background by Gringarten and coworkers back in 1975. And what you're looking at in the plot in the upper left-hand corner are a series of thermal decline type curves where you're looking at dimensionless water temperature versus dimensionless time for various fracture spacings. So the concept's been around for a while, and the industry's just leveraging innovation to make this a commercial success today. If we look at the bottom illustration of two wells with fractures, and if we look at this from a gun barrel view, obviously we're creating hydraulic fractures that are intended to connect those wells. In the case of Utah Forge, the wells are vertically stacked. In other commercial applications, for example, Fervo, it'd be more of a wine rack type of pattern. Obviously, we're going to create a fracture and place proppant somewhere inside that system. For EGS, what we're really concerned about is the surface area that's being swept for heat transfer from the system. So we're looking for this turquoise area, the fracture circulation area. Obviously, we have a lot of fractures along the length of that wellbore. Each of those fractures can have a different surface area and a different flow rate, and those appear in the Gringarten solution. So we need to understand that ratio of flow rate to surface area per fracture in order to understand the heat transfer capacity or capability of the system for energy production. So what we're going to show you today is that with the use of tracer technology, we're able to get the distribution of flow rates per fracture in the reservoir, as well as the surface area of the system. And that together allows us to solve for the Gringarten solution and provide the economic life per treatment stage. So why is it important on a per stage basis? Well, in Utah Forge, they've varied the completion and stimulation design along the lateral to help optimize and understand the impact of technology. So obviously understanding a stage level performance allows us to understand the impact of the designs. The second thing is that, generally speaking, we'd be looking at a circulation test until breakthrough, thermal breakthrough, in order to assess the economic life of a system. And that can take months to years, where the circulation tests that were performed in Forge were done for about 28 days, and we're able to assess the economic performance from that short-term circulation test. In other words, we've accelerated the learning curve. So we'll show you how we got to these solutions as we walk through the presentation today, and then characterize the flow system between the two wells. So a little background on Utah Forge. You can see the photograph in the upper right-hand corner with a projection of the wells in the dashed lines. You see the well trajectories in the bottom profiles. Just a little history here. So in 2021, the blue well, injection well 16A, was drilled into the formation. These are inclined wells to enable gravity logging. In commercial applications, these would be truly horizontal. So you can see they drilled the 16A well, and they performed 3 fracturing stages near the toe of that well. They monitored with microseismic, and then they drilled the 16B well in red through the microseismic cloud. And then they performed some circulation tests to assess that connectivity. In 2024, they went back out and added 8 hydraulic fracturing stages along the length of the blue well, and that's when Resman started getting involved in the project with tracer technology. So we traced each of those 8 fracturing stages, and then the team performed circulation tests between the 2 wells, and we included tracers in those circulation tests as well. I want to highlight that the bottom hole static temperature here is about 430 degrees Fahrenheit. As I mentioned, as part of this research endeavor, a lot of parameters were varied. You can see a list of some of the key parameters from a completion and stimulation perspective here. The number of clusters per stage was varied along the lateral. There was variability between cross-link CMHPG and slick water as the fracturing fluids. There were also some challenges that came from the reservoir itself. So stages 6 and 7 in the 16A well had rock property variability, which resulted in inability to get frac rates per design. So those stages were fractured, but proppant was not pumped in stages 6 and 7. The team also did small frac stages in the 16B well based on fiber optic that was in the 16B. They identified frac hit locations, then perforated it in small fracs to make sure the fractures were connected to the production well. In the last stage in that well, it was only perforated and not fractured. So we have variability that was part of the design, as well as variability from the reservoir or the operational aspects that we're looking at across the project. And again, we're using tracer technology to assess that. And we're looking at this from a perspective of extracting quantitative information. And to do that, we need to deploy tracers based on 5 core pillars to ensure quantitative delivery. So the first pillar is the chemical technology itself. So it needs to be inert and pure. And that's something that obviously a lot of quality control goes into play for the tracers themselves. 30 unique chemical tracers were injected in Utah Forge. These are inert, non-hazardous, non-radioactive, water-soluble tracers. The second pillar is around controlled operational deployment. It's essential to do for quantitative interpretation that we know the concentration of the tracer in the fracturing fluid that we're being produced. So for that, we're relying on controlled deployment. And this is a flexible delivery method that aligns with operations. So it's not intrusive to the fracturing process. The third pillar is the sampling. So we're looking at more than just yes or no, the tracer came back. We're also looking at the shape of the tracer response curves in order to extract information around the subsurface. So that just means strategic sample timing. And we're collecting samples in this project from both the treatment well during post-frac flowback and from the offset well during production. The fourth point is around cutting edge analytics, and Resman is leveraging advanced biotech and medical laboratory capabilities for the analytics, and that allows them to bring parts per trillion or higher detection level. So a lot of capability now to leverage the tracer response curves for advanced interpretation, which is the fifth pillar around interpretations that are based on fundamental physics. So we stay true to those five pillars, we're able to extract quantitative information from tracers, and that's what we'll focus on here today. Just a little background on the qualification of the tracers for geothermal applications. You can see an example in the top right with the bar graphs that's showing thermal stability tests in the laboratory for 3 tracers at temperatures up to 460 degrees Fahrenheit. And you can see here that tracer A and tracer B passed that qualification for up to 90 days, whereas tracer C failed that test and was disqualified from the program. We also do co-injection of tracers to verify performance in the reservoir. So here you can see a couple of examples within stages in Utah Forge, where we had multiple tracers deployed simultaneously under the same deployment scheme, and we're seeing the responses come back consistently. These 2 plots represent 3 different chemical classes of tracer that were deployed in the project. So in terms of the overall interpretation, we already mentioned 30 unique chemical tracers. The other unique thing is that there were 3 different deployment methods for the tracers. Tracers were deployed in the fracturing treatment itself, as well as pulsed in the fracturing treatment. And then we had tracers that were pulsed during the circulation tests. So 3 independent types of deployment. And then there were 4 different types of well operations that we were monitoring across. And that included flowback of the 16A injection well, offset well fracturing operations, the milling process in the 16A well, as well as during the circulation tests. All of that together leads us to about 20 answer products that fall across quantitative production log, where we get a distribution of flow profile along the well as a function of each sample bottle that we collect. Fracture-driven interaction or frac hit characterization that's telling us more than did we just connect, but what are the significance of those connections over time. We're looking at fracture characterization, where we can assess things like fracture conductivity, porosity, and complexity of the flow system. And then the fourth is around flow efficiency, where we're focusing in on trying to understand that reservoir contact area that's so important in EGS for enthalpy extraction. So we'll start by focusing in on the quantitative production log. And to illustrate the foundation of this, what you're looking at here are the tracer response curves. On the vertical axis is concentration in parts per billion, and the x-axis is the cumulative flowback or produced volume from each of the wells. In this presentation, everything you see on the left-hand side of the screen will be related to the flowback of the 16A well, and data that you see on the right-hand side of the screen will be related to production from the 16B well during circulation tests. What you see is a lot of data. We detected all of the tracers that were injected into the reservoir we've detected in the project. And that includes after more than about 4 months in the reservoir at that 430 degree Fahrenheit condition. So the first thing you probably notice is there's a lot of spikes in the data. And these are related to operational changes. And we'll get into some of the details of those operational changes. and how that helps us for interpreting the subsurface properties. Um, as we go into this, we'll go into some of these different arrows and highlight kind of the performance. The other thing you notice on the circulation side, we've got the concentration of the tracers that were injected in the frac stages, and they're being produced out of the production well over time. And you can see those results in April and August. And that spike in the middle is due to an extended shut-in period between those two circulation tests. And we're not going to talk about that aspect today. So to start looking at this, we're going to focus in on two areas. One is at the end of the flowback period after the frac plugs have been milled from the system. These are all flow-through plugs. So throughout the flowback process, we're able to detect the performance of the system, but we're going to focus in at the end of this after the plugs are milled. And we're going to compare that to the first circulation test that was conducted in April, and that's about 5 days apart. So if we look into that data, we can now look at the quantitative production logs. These are the percent flow contribution per stage along the vertical axis. And along the x-axis is the stage and the number of clusters that were treated across those various stages. So looks very similar to a production log, a PLT that you may see with a mechanical log. So you can see the distribution with the percent flow contribution, for example, 38% of the flow coming from stage 9, about 15% from stage 7, etc. You immediately see that stages 6 and 7, where, as I mentioned, we didn't place proppant from the 16A well, they are still contributing to the flow, both during flowback and circulation. So although we didn't get proppant into the system, those fractures that were created in those stages are contributing to the flow of the subsurface system. The other thing to highlight is these are very different flow setups, right? In the flowback, we're basically pulling fluid from the fracture system and out the treatment well, whereas in the circulation test, we're injecting in the 16A well through the connections and out the 16B. And it's interesting that the two quantitative production logs are very consistent in those two cases. So that tells us we've got very good hydraulic communication between the wells, a key objective for EGS. The other thing to highlight here is that each of these vertical bars is from a single sample bottle. So we pull one sample bottle and we get the distribution of flow across all the stages in the well. So each vertical bar is a different sample bottle over time. So here we're looking at quantitative production logs and how they change with time over about 4,000 or 2,000 barrels of production on these two plots. And then we can compare all of this to lots of parameters in the project. For example, here we're overlaying treatment design properties. So the gray bar is the number of clusters per stage. The bright blue bar is the volume of treatment fluid that was pumped. And the tan bar is the mass of proppant that was placed. And what you see is we've got pretty good comparison between the trending and the treatment volume, for example, in bright blue, and the quantitative production log from the tracer response. That's true across most of the stages, except for stage 9. We see a big discrepancy between, the performance from the QPL, producing, a higher percentage of flow than we may have expected based on the treatment volume. And we refer you back to the ERTEC paper. The root cause of this was linked to cluster runaway. In other words, not all of the clusters were treated uniformly in stage 9, and we had a couple of the clusters dominating the treatment. And that seems to be very consistent with the response we're seeing, and that was validated with a couple of other different methods. So I refer you back to the paper if you're interested in more details there. But basically, we see signatures of cluster runaway from the tracer interpretation as a result of that comparison. I mentioned, we have lots of variability in operations along the course of this project. What you're seeing is the QPL we looked at before during flowback. Again, that's after the plugs were milled. So now we're going to add another section of the QPL to this. We're looking in at a section of the flowback where there weren't a lot of operational changes, and we can see, the gray bars while we're flowing through the plugs and the bluer bars after the plugs are milled. And we see that across the flowback, we're getting contribution from all of the stages through those flow-through plugs. At the start of flowback, while we're flowing through the through plugs and after plug milling. What's interesting here is we're having operational changes now as part of the data set we're looking at. And we can start to see significant changes in the data as a result of that. And I'll focus in on just a couple of them to illustrate the point. You see a big step change in stage 6 from before and after we were milling the plugs. Because we have the detail from the QPL, we can go in and see exactly what caused that step change. And it was actually a step change that occurred when we milled the plug above stage 7. So we believe that's related to a change in the bottom hole pressure that affected how the toast stages were flowing. And that could be used to then diagnose the safe operating window as a function of the treatment design on a per stage basis. The other thing you see is if you look at stage 3R, we see a spike in the quantitative production log. That corresponds directly to this gray shaded region where we were fracturing the offset well 16B in the first stage. So we can see that response show up in the flowback of the 16A well. So we can extract a lot of information from those operational changes, and I'll show you how we do that with an example here. So we're going to take this quantitative production log and we're going to convert it into what we call a dynamic response function. So basically, if that value is 0, there's been no change as a result of the operation. If that dynamic response function increases, that means there was a fracture-driven interaction as a result of the operation associated with fracturing stage 1 and 16B. And if it declines, it means that those stages were diluted, the tracer was diluted as a result of the volume that was introduced from this FDI. So when we look at the data set, we see that several of the stages in the toe, stage 3R and 4 through 7, all had a positive indication on the dynamic response function over the course of that operation in stage 1. And correspondingly, stages in the heel section were diluted, and we see the negative spike. So we know there's now hydraulic communication between those stages, and we can capture that in terms of this illustration on the right-hand side. We now have proof of hydraulic connection between stages 1 and 16B and stages in the toe section. So those lines now represent at least one hydraulic flow path connection between those sections in the reservoir. We can repeat this for all of the operations across the well, and we can construct what the flow path connections are between the two wells. And because this is based on the quantitative production log, we also know the volumes of each of those interactions. So we know the volume that went through each of these sections during those fracturing operations. As I mentioned, we only perforated stage 5 and 16B. It wasn't fractured. So as a result, we don't have data to do this analysis on stage 5 and 16B. So now we have a representation of the hydraulic flow path connections between the two wells. So we'll compare that now to fracture corridors that were determined based on fiber optic data. This was published by England et al. Earlier this year. So what you're looking at in the plot on the left are results from having fiber optic in the 16B well while we were fracturing the 16A. And they drew polygons connecting where the frac hits were in the 16B relative to the stage that was being treated in 16A in order to connect or create a fracture corridor map. And you can see that the two look very consistent. So we have likely fracture corridors from frac hits from the fiber optic data, and we have flow path connections, hydraulic connections from the tracer data in the plot on the right. So with the flow path connections, we can now go back in and start comparing the quantitative production logs to other measurements we have in Utah Forge. And we're going to make a comparison now between the QPLs and mechanical PLTs that were run in the well. So we have a direct comparison. We have the quantitative production log in the 16A well. In order to look at the 16B well, we know what fractures are flowing, but we don't know where, from the tracer data, we don't know where they're connected in the 16B well. So we're going to map the quantitative production log that you saw before to the 16B frac stages based on the flow path connections we just talked about. And when we do that, we get this cumulative flowback log along the length of the 16B well that's representative of the tracer response through the various stages. And now we can compare these two data sets to mechanical logs, and those are overlaid here in yellow and orangish colors. First thing to highlight, the mechanical logs, none of them reached the toe. So you can see that we had a couple injection logs that reached stage 6 and stage 4, and in the production well, it reached around stage 3. So in order to compare these, what we're going to look at is the toe of the well versus the heel of the well. And when we make that comparison, we see that that across all of these measurements, the heel section is producing about 65% of the flow compared to about 35% of the toe. And that is consistent across 5 independent measurements across the project. We also seen some interesting trends on the data set. For example, with the yellow mechanical log, we see that in the April test, it's very consistent to the flow contribution from stage 9. We see that that changes over time and decreases to orange at a later time in August. And at the same time, the orange bar is increasing in stage 10. That occurred over a time period where the flow from the fracture, as indicated by the tracer data, wasn't changing. So we know we have some redistribution or reconnection of flow paths in the reservoir. So the system's changing over time is what this is telling us. The entry point has changed, but the same fractures are being swept. So we have an interesting comparison now with 5 data sets giving a consistent toe heel kind of split. So what we talked about so far is the quantitative production log and how we used it to understand flow path connections. We're now going to go a bit deeper and start characterizing those fracture-driven interactions and the fracture itself. So from the FDI perspective or a frac hit perspective, we know the connections, and these 2 plots here are for illustration, but we're generally used to seeing plots where we see where the tracers injected in a particular well are recovered, and that gives us insights on what connections exist in the subsurface if you think of this as an illustration of an unconventional field with different benches that are being completed. So we can use that type of information to understand frac hits and connectivity. But since in our project, the tracers are deployed quantitatively, we can extract a lot more information from this. We can extract the volumes that are connected. We can characterize the systems. So I'll show you a few examples of what we do. So first, this is the quantitative production log we saw before. This is now normalized by the number of clusters per stage. And we can use that to look at things like uniformity bias. In Utah Forge, we see that the flow is biased towards the heel section of the well and underperforming in the toe section, right, on a relative per cluster basis. This is an extremely important plot for EGS because we want very uniform flow across all of the fractures to avoid some of the stages taking more fluid and cooling down and having thermal breakthrough sooner. So this is a key deliverable for EGS, being uniformity bias. The other thing we can look at is connectivity bias, and this is understanding the balance between the 2 wells. So what you're looking at is the percent, it's kind of a flux measurement, if you will, the flux in the different directions in the system. For Utah Forge, this is a comparison between production and flowback, and the length of the red bar, for example, is pointing towards a flow restriction near the 16A well in stage 6. So we can see, obviously, without having proppant there, it's more difficult to flow through the 16A side of the well. In an unconventional reservoir, you can think about this as like a continental divide. It'll tell you kind of where the formation balance is between the 2 or the various wells in the system, and tell you how well the frac spacing is enabling drainage of the reservoir. We also look at durability, or how significant these connections are over time. So a lot of cases, a frac hit may show up, but if that frac hit pinches off, then it's no longer significant for any production performance of the system. So we use the tracer interpretation to diagnose the durability of the various stages over time. So what we can see here is anything in the orange box are declining durability, and anything above the line are stable or relatively speaking, increasing. So we see the highest durability in the system is coming from stage 8 that was treated with CMHPG. We see declining durability in stages 6 and 7, which didn't have proppant. And we also see it in stage 9 where we had cluster runaway. And we believe that's due to the non-dominant clusters kind of pinching off and not contributing as significantly over time. So we now have three metrics that we can quantify the significance of fracture-driven interactions and what they mean to the flow system, the production over time. To go into this a little bit more detail, we're going to look back at this percent flow contribution per cluster. Here we're just looking at those for the two wells. And what's interesting to note is over the course of these operations, there were actually changes in the flow rate. So during flow back, the surface flow rate was declining over time. And during the circulation test, the flow rate was increasing over time. So now we have another case where we have quantitative production logs over the course of operational changes. So again, we can use that to diagnose the system. So what we're going to look at now is what we call the proppant transport capacity. And we extract this from a plot of the flow rate per cluster on the vertical axis. That's simply taking the QPL multiplied by the surface flow rate to give us the flow rate per cluster over time. And for those flow rates, we have the corresponding injection pressure. So we've calculated the bottom hole pressures for each of the stages for those corresponding rates. So now we have a plot that we can apply Darcy's law to. And from Darcy's law, the slope of this plot is conductivity times the width of the fracture face divided by the viscosity of the fluid and the length scale, which is in Utah Forge, the distance between the wells. So we can, from the slope, extract this parameter. So we're going to define what we call the proppant transport capacity, which is an indication of the ability of the fluid to carry and transport proppant. That depends on a lot of parameters. It depends on the viscosity and the rheology of the fluid, the density and size of the proppant, obviously the fracturing treatment flow rate, the fracture geometry that was created, and things like surface asperities along the fracture face. So it depends on a lot of parameters that we may or may not have control of, depending on what it is, right? So we've defined the proppant transport capacity as the product of the permeability times the permeability of the fracture times the volume of the fracture. So the aperture, the width, and the height. So the surface area of the fracture, the aperture, and the permeability, which is conductivity times the surface area of the fracture, which from our diagnostics plot over here is the slope times the viscosity of the fluid and the distance between the wells squared. So we've got a direct measure now of the proppant transport capacity from this tracer diagnostics in the system. So if we zoom in and focus in on stages 3, 4, 5, and 8, this is a comparison between slick water treatments and CMHPG. The vertical axis here is this proppant transport capacity. We've just normalized it by stage 4. So stage 4 comes out as normalization of 1 to emphasize the percent differences. And what we see is about an 18% higher proppant transport capacity for the two stages here that were treated with CMHPG versus slick water. I should also highlight that the CMHPG stages also had a little bit higher max PPA. That's 1.5 PPA for CMHPG compared to 1 PPA for slick water. So there's two things that are varying, the fluid and the amount of proppant. But with those changes, we're seeing an 18% higher transport capacity with a treatment design we would have expected to have better proppant transport. So we can see that difference with the tracer data. Obviously, this could be influenced by heterogeneity in the subsurface as well. But the point is that we've got treatment designs that we can detect differences in the performance from the tracer data. So we've started talking about, characterizing FDIs and fracture properties. We're now going to add to this interpretation data from the circulation test for flow efficiency and use that to enrich our characterization of the subsurface. So this data is now coming from the circulation test where we're injecting into the 16B well and producing out the 16A well, and we're adding pulses to that injection fluid. And this is done over various flow rates. So they did flow rate steps from 2.5 up to 10 barrels a minute. What you're looking at in the plot in the top right-hand corner is the residence time distribution of that tracer. And you can kind of think of this as the tracer concentration on the vertical axis versus time. And you can see how the pulse is going through the system and coming out. What you're seeing in that residence time distribution or RTD plot are the last two tracer pulses, both performed at 10 barrels a minute. and we're seeing the RTD response for those. And we can see the two are very consistent. In other words, we're getting a very consistent flow distribution through the fracture system. The apex of this plot is the flow volume of the dominant flow system in the subsurface. And we know the volume of that is 4,680 barrels from the RTD interpretation. So we now know the volume of the circulated path, the dominant path through the flow system across all of the fractures in the system. So 4,680 barrels. Since we have the QPL, we know how that is distributed across the various stages. So we now have an understanding of the volume of these flow paths in each of the stages. This is volume. For enthalpy extraction, we want to get to surface area. So we did a aperture sensitivity analysis to get to a range on the surface area. So what you're looking at in this plot in the bottom left-hand side is the effective aperture of the fracture. So that's average over the flow system for the various stages. And we've got some max and min ranges on this. So the gray bar is the maximum aperture, and that's based on fracture simulation modeling for Utah Forge, published by ResFrac. And they reported a value of about 0.12 inches between the wells. So that's the maximum aperture we could have. We then used some calculations from the tracer response to get the minimum. And this is based on using the residence time distribution and the distance in the wells to define the cross-sectional flow area. And we just need to define one other length scale. So we use the microseismic data, and from the cloud of the microseismic, we got the maximum width of the fracture. In other words, the maximum length of the fracture. So this cross-sectional area divided by the maximum length of the fracture from microseismic gives us the minimum effective aperture. So now we have a min and max range on the aperture. We took a weighted average of that to give us the turquoise bars, which comes out to 0.07 inches as the average width for the fracture, aperture for the fracture. So with that, we can now calculate fracture surface area. And you can see how that varies across the stages. The bars are in turquoise are based on the 0.07 aperture average from the sensitivity analysis, and the error bars are based on the min and max sensitivity range on the effective aperture analysis. So now we have some understanding on what that surface area per fracture will look like. And obviously that's a key input into understanding the enthalpy extraction of the system. We compared that to microseismic data. We can see that if we just look at a conservative estimate of the area of the cloud, the surface area that we're treating is about, on average, 20% of the microseismic cloud that we see in the system. In other words, the area of this turquoise is about 20% of the conservative estimate of the fracture geometry. So I want to highlight a couple other things. So if we go back to the RTD analysis and 4,680 barrels, that's an interesting look at the effective porosity of the system. If this was a conventional proppant pack with grain-to-grain contact and 35% porosity, the pore volume of that would be about 1,758 barrels. We have a flow system that's about 3 times larger than that. So it's clearly not flow through a conventional pack. If we looked at this on a big picture, it'd be about the entire system average would be about a 59% effective porosity. But we can look at this on a per stage basis. So if we look at the proppant pumped in each of the stages, we can see the effective porosity per stage. And you can see it's up around 83 to 96% in stages 7 and 6. Those are the stages we didn't pump proppant in. So we can expect that to be very high. We did pump proppant from the 16B well. That's why this is not 100%. But the point to highlight here is this is not representative of the system. This would assume that 100% of the proppant is between the flow paths and in between the two wells. So it's not realistic to have 100% of the proppant between 16A and 16B. So we use the fracture surface area percentage of 20% we just talked about to estimate the amount of proppant that would potentially be between the two wells or in the flow path. And when we do that, we get this effective porosity that on average for the system is about 82%. So this is our first known measurement of effective porosity in a propped fracture on the subsurface. And this is very different than a conventional proppant pack system. These are very high effective porosities, suggesting we've got a very unique flow path system. If we look at this relative to partial monolayer coverage, that would be around 60 to 62%. So we can see stage 4, 5, and 3 are reasonably consistent with partial monolayer coverage, but we have very high effective porosity in the stages with a higher number of clusters per stage. There could be a wide range of mechanisms for that: natural fractures, partial monolayer, a lot of arch or channel structure formation, and the impact of surface asperities, or some combination of all of those. And just as a simple illustration, you can think of potentially a duning scenario where a lot of the proppant from the 16A well duned or settled below that well, leaving arch structure above it. So a lot of potential mechanisms to explain this, but the point is that it's a very different flow system than what we would think about for a conventional proppant pack. This now gives us all the details we need to calculate the conductivity. So we have the flow per fracture, we have the porosity, we have the volumes, and we have the aperture. So we now have data to calculate the conductivity per fracture. The turquoise bar is again based on that 0.07 aperture. The dark bar and the light bar are the ranges from the low end and the high end of the aperture sensitivity range. If we look at this compared to natural fracture conductivity data for slick water treatments, we see it falls in the expected range we typically see in a shale treatment. And we're just plotting this relative to some data with Jordan sand and 0.1 pound loading. And it seems pretty reasonable for the designs in terms of what we're measuring in the subsurface. If we focus in again on stages 8, 3, 4, and 5, we can compare again slick water to CMHPG. We're seeing about a 25% higher conductivity when we compare those two design types. And if we think back to now that proppant transport capacity, we now have two independent measurements that are showing differences in the frac design in terms of subsurface performance. The conductivity is obtained from the QPL and the RTD analysis, where the proppant transport capacity is from the QPL over changing operations. So two independent measurements giving us a diagnostics of design changes impacting the subsurface. So now if we go back to where we started, we started with Green Garden, and we've now seen how we got the quantitative production log for flow and surface area. And that gives us the economic life of the system. And we can see that for stages 6, 7, 9, and 10, that's about 3-year economic life before we would get thermal breakthrough in those stages. We can do lots of comparisons with the system treatment designs. So this is just a plot of economic life versus the mass of proppant per stage. And as you can see, more proppant is longer life. So it's showing, again, a benefit of adding more proppant. Turns out the root cause of this variability is actually the uniformity bias. And we can see that the uniformity bias is directly controlled by the fracture conductivity that we've created. So a very strong trend between uniformity bias and fracture conductivity. And you can see our stages with CMHPG and slick water that we've been comparing, compared to stages 6, 7, 9, and 10 that are a bit higher in conductivity, but these are likely dominated by formation properties, by cluster runaway, and by no proppant. So in other words, asperities. And if we go back and look at the conductivity study, basically, we can see we're in a pretty narrow band where a factor of 2 in our conductivity gave us a factor of 3 in economic life. But if you look at that red circle, that's the variability we could get just because of the variability from Mother Nature in terms of conductivity. So that raises some questions in terms of design optimization. We have plus or minus factor of 2 in conductivity in Utah Forge that gave us an economic life of 3 years, where in a real formation, variability potential is a factor plus or minus 100x. So what does that do to economic life? That really raises questions about how we overcome basically this variability from Mother Nature. And to me, the answer is proppant placement. And you can just see an overlap here of 1 pound of Jordan sand overcoming that dependency. So back to thinking about how to optimize treatment design. So with that, I'd just like to thank, and acknowledge that this work was funded by Department of Energy under the grant for Utah Forge. And with that, I'd be happy to answer any questions.
Thank you, Chris. Really provocative discussion. And we do have a few questions that are posted. I don't know whether you can see them. I can read them. First of all, Paul likes the designation of fractured corridor. And he finds it a new term and he likes it. Is there anything that you'd like to say more about that?
Yeah, I think the fracture corridor kind of metric that came from the work by England et al., where it was using microseismic data to show uh, the stages that were initiated and where those hits occurred to define a corridor. Yeah, so that's illustrating somewhere between those 2 points, there's a fracture hit. And then from the tracer data, we were able to verify that not only were those hits, but those are hydraulic connections that maintained flow paths during the circulation process in Forge. So yeah, I
Good.
think lots of opportunity to leverage that to understand flow paths in the subsurface that we don't really think about a lot now. We take for granted that the fracture is producing.
Indeed. The next, there's a couple of questions from Luke Frash, and Luke's first question is, can you comment on the bottom hole injection pressure during these flow tests and how it might compare with the inferred minimum principal stress?
Good question. I didn't compare back to the minimum stress. I know there were some questions about one of the higher rate circulations, whether that was getting pretty close to the minimum stress, but I didn't make that comparison. That's something we can go back and take a look at.
Actually, I might step in there. Is that the injection pressure, Luke? We tried to control it to prevent fractures from propagating. Whether we were successful or not is another story. And here's another good question from Luke. He's asking, you mentioned of coming up with thermal performance forecasts from short-term tests. Can you elaborate a little bit more on that?
Yeah, so that's coming from the solutions from Gringarten and coworkers. So basically, we used the dimensionless water temperature of zero point 0.2, which is common for conventional geothermal operations. So if we make that assumption, we know the spacing in the system, and we can define a dimensionless time of 1 based on the frac spacing, and hence we can use Gringarten's equations to calculate the economic life on a per stage basis. So the value of that is that we only need the surface area and the flow rate per fracture in order to determine the economic life. And both of those parameters we obtained from the tracer interpretation. So the end result is a circulation test with tracer over a short time period can be used to diagnose the economic life of the system because we have the surface area and the flow rate. So we don't have to wait, 3 years to see thermal breakthrough in Forge. We have it from the tracer interpretation and Gringarten's thermal decline.
Okay. And then Trenton's question is, when were the distinct tracers added to each of the stages? I mean, was that during the fracturing only, or what percentage of the tracer, and also what percentage of the tracers pumped was recovered?
Yeah, so the percent tracer pumped, that varied depending on the stages, obviously, but the general range was between about 30 and 60% of the tracer per stage being recovered. That was a total mass recovery percentage over the project. In terms of deployment, we had 3 different deployment methods. So each of the frac treatments had a mass balance tracer in it. By mass balance, I mean we traced the entire stage and we controlled the deployment so that the concentration in the treatment was maintained the same. In other words, as the clean fluid rate changed, we changed the additive rate to maintain a constant tracer concentration across the frac stage. In addition to that, we added pulses into some of the stages. So we'd add a pulse of tracer while we were fracturing, and we used that for some advanced diagnostics that will show up in a follow-up publication. And then we had pulses that were in the circulation test. So while we were circulating at different rates, we were pulsing tracers there as well. So the quantitative production log is built on those mass balance tracers with known concentrations in the fluid.
And Joseph is interested if you would comment on using limited entry on the clusters.
Yeah, so I think there's a lot of questions from the EGS world in terms of what that does to parasitic losses. Certainly, from a fracturing perspective, if we're thinking only about frac construction, we would like limited entry to make all of the perforation clusters break down and treat as uniformly as possible. A lot of debates on how well that may or may not work. I've looked at a few data sets in EGS. The uniformity bias plot that we have for Utah Forge varies between plus or minus zero point 0.5. I've seen other projects where it varies by 2 to 3 times more than that, even with limited entry approach. So a lot of questions about how effective that really may be. But certainly from the fracturing perspective, we need to do something to make the fractures treat as uniformly as possible across all clusters.
And and Jeff is interested in more information on Resman's tracers that worked at 400 degrees C. Is there anything you can comment on it? And Jeff, I think Chris can provide you the provider and contact information.
Yeah, so we can get you in contact with the team at Resman. So as I mentioned, there were three different classes of chemicals that were used in Utah Forge. One of the classes we included just the typical NDS type of tracers. The other two are proprietary. There are probably about 40 tracers and many in the pipeline for geothermal applications. And we're getting ready for application even in the 350 degrees C range with some of these tracers. So I'm happy to get you in touch with the Resman team for more insights there.
And so Yegor is interested in talking a little bit more about the fracture corridor. In particular, it was shown that the fractures are non-vertical and hit the observation well at an angle. Is there hard evidence for this?
Yeah, so good question. I think that's coming from just the connections and the positions in the well. Yeah, I think we can probably go back and look at the microseismic data, but there is a bit of a change in the going from sub to more vertical along the length of the lateral if we compare toe versus heel section of the well. So we do see differences in that vertical nature of the fractures from microseismic that comes across from the fracture corridor drawings that were done based on fiber optic. From the tracer data, obviously, we can't say anything about the orientation of the fractures, but the data sets are pretty consistent.
And then the final question that we have up to this point is, Romain, in found it was informative, and can you connect on the mass balance of the system between injected and produced volume and how it varied between clusters?
So we didn't go back and look at the mass recovery relative to the treatment design. So that's something we can probably take a look at. I guess that would come across in the connectivity bias. So my first impression, we're not seeing a big trend because the connectivity bias was fairly balanced across the wells, close to 50% for all stages except six. So we can go back and look at that, but my gut feeling based on just the connectivity bias is we're not seeing a strong dependence on the mass recovery percentage versus the individual completion design.
So,
Would also
sorry.
like to add to that, right? So there are operational changes, and because of that, the QPL or the quantitative production log changes from sample bottle to sample bottle. When we look at just the cumulative mass recovery, which is a typical metric used in multi-stage fracturing diagnostics, that's averaging it over all of those operational changes. So mass recovery is influenced by all kinds of changes in the well. When we compare a distribution of flow from a mass recovery to what we see from a QPL, the error bar on that relative to the QPL is very significant. So we can have upwards of 100% error in what we think the flow contribution is on a per stage basis, depending on how we use mass recovery methods. So just a word of caution if you're using that for flow distribution with typical deployments not aligning with the five core pillars, that introduces quite a bit of error.
Luke has another question, and it's one that you've heard before. What data or information do we have to evaluate whether or not it was in 16B it was flow behind casing, or well on either well whether there was flow behind casing?
Yeah, at this point we don't have data to say one way or the other. In fact, let me go back to one of the plots. So when we do the dynamic tracer response analysis, we are seeing quite a bit of connection. You can see this light blue dashed line for stage 7. So we see stage 7 respond to the dynamic response function across multiple fracs here. So that we can infer is there's some type of connection. What we can't tell is whether that's a leaking plug, and the reason the tracer showed up is just leaks through the plugs in the system, or whether that's a microannulus or connections through the fracture. So that line is dashed because we have no idea where that connection is, but there are clearly connections from stage 7 all the way from 8 to 3R. Whether that's microannulus, leaky plugs, or natural fractures, yeah, we need other diagnostics to help answer that.
And then the final question we have is from Chris, and he said, "Great presentation, Chris. And maybe I can help you with this answer. Are there plans to perform a long-term circulation test at Utah Forge to validate your prediction of approximately 3 year for thermal breakthrough?" Um, and so the upcoming plans for Utah Forge, Chris, are that we will do a 3+ month circulation test starting in September or so to see what happens over 3 months. And then there'll be some drilling and more fracking, and then there will be an extended circulation test. It's unlikely we'll be pumping for 3 years, but we are extending the circulation tests to try and see about thermal breakthrough. So, Chris, I'm going to give you the final word. Chris Fred, I'm going to give you the final word. And
So, I think from my perspective, what we see is a system very different than we're typically used to thinking about for hydraulic fracturing. And it really, for me, comes back to this. We know that Mother Nature is not uniform. And we know that from a EGS perspective, we want to minimize any variability from fracture to fracture. In other words, we want the uniformity bias to be zero. So we need some way to make sure that we're mitigating Mother Nature, if you will. This plot's just highlighting that Mother Nature can vary by about three to four orders of magnitude just based on where and how the proppant is placed. Frac design conditions can overcome this. For example, pumping higher concentrations of proppant mitigate that variability, or using high strength proppant. So in my mind, we're focused in on slick water designs from the oil and gas world, when I think we really need to be thinking about overcoming this variability from stage to stage that's going to come from asperities and natural fractures and all of this type of risk. And that, I think, the only answer based on what we're doing today is more proppant and thinking very differently about the frac design. So my comment is think out of the box relative to unconventional oil and gas.
well, we're just about on time. Well, we've got 1 more minute, but nevertheless, Chris, thanks for a very, very provocative and insightful presentation. And for those online, if you've got additional questions, do not hesitate to reach out to Chris. If you don't have his contact information, just drop me a note. So thanks, everyone, and we'll see you in a couple of weeks.
Thank you.
Hey, every time I learn something, man, I get more questions every time. But yeah,
That's a
really,
very rich data set, right? I mean, it's amazing with all the measurements that were done, what you can really see.
yeah, yeah. Ultimately, we're going to have to plan another fracturing campaign, and that's probably not, that's a year out, I'd say. You're
Looks like we're still recording, eh? You want to give all your Utah Forge secrets away?
there's no secrets, but I can stop.